And next up, we have Seiji Fujimoto. So we could transition to Seiji's slides. Seiji will be talking about the ALMA Lensing Cluster Survey today. So take it away, Seiji.
Okay, so hello everyone. First of all, thank you, organizer, for introducing me and giving me this wonderful opportunity to be here. So today I will talk about the great outcome from ALMA large project called ALMA Lensing Cluster Survey, especially about the first achievement of spatially resolved ISM study for a typical sub-L galaxy at redshift 6. In the later part of my talk, I will also introduce about our JWST program scheduled in cycle 1 related to this ALMA survey. So first, the motivation. The early galaxy evolution is regulated by several key mechanisms taking place in the ISM, such as clump and disk formation, stellar feedback, and mass building via star formation and mergers. To address such a detailed ISM picture of early galaxies, recent ALMA studies have detected the ionized carbon emission, which is one of the helpful Coulomb lines tracing the cold ISM. But a large diversity has emerged. Some are brightly detected, while others are not, or sometimes it shows significant offset from the stellar continuum. Several causes have been discussed, but one important fact is that ISM property can be largely different even within a galaxy. So here is a high-resolution ALMA line observation towards SDT81, a famous strongly dense dusty starburst galaxy at redshift 3. And it also finds that line luminosity normalized by fine-infrared continuum varies by almost 2x scale within the galaxy. So although ALMA has nicely offered the line detection from early galaxies, now we should move on to spatially resolve this detection, characterize the localized physical property of the ISM, and understand what the key mechanism is taking place in a typical galaxy in the early universe. To overcome such a small size and faint property of such typical early galaxies, the gravitational lensing is essential. So including this context, a large unbiased ALMA survey has been carried out. Using 100 hours of the ALMA large program time, we map out 33 massive lensing clusters by setting up 2 frequency tuning, which maximize the detectability of not only the continuum sources, but also the line emitters. And we achieve a total area of 100 arc square minutes with a moderate data depth, but the average sensitivity after the lensing collection is almost comparable to the previous deepest ALMA surveys. So here we compare the area and sensitivity of the ALMA large surveys so far performed. So after the lens collection, the parameter space in our ALMA survey is like this. So ALMA Lensing Cluster Survey explores the faintest regime, both in the depth and area, which provides us with unique objects that couldn't be identified in previous surveys. Moreover, independent line of sight towards 33 massive lensing cluster are helpful to overcome the cosmic barrier. As a result, we are identifying the hundreds of continuum sources, tens of line emitters, and even several lens near-infrared dark galaxies that are bright in ALMA, but are not detected at all in all HST bands or even sometimes Spitzer IRAC bands in some cases. And what is more, we discovered very interesting bright line emitters at redshift 6, which is the main topic of my talk today. So here summarizes the ALMA spectra and the line intensity in red contour overlaid on the HST map. So we detect these 2 bright line and 1 tentative line at the same frequency, exactly at the position of redshift 6 Lyman-break galaxy. These LBGs show a similar SED shape, and the peak of the redshift photometric redshift distribution are in excellent agreement in the case that the C2 the line is interpreted as the C2 line at redshift 6, shown in the red line. In fact, this redshift solution is confirmed with the latest JWST spectroscopy, where we see the continuum break at the expected wavelengths. So we determine the redshift, and based on this redshift solution, our independent mass model consistently predicts that these LBGs are multiple images from one galaxy. So based on these results, we conclude that these bright lines are multiple images of the line emission from a galaxy that at redshift 6 behind the cluster. And remarkably, not only the C2 line, the observed H-band magnitude is also one of the brightest so far confirmed at redshift over 6 among the star-forming galaxies, so suggesting that this system will be a unique laboratory for detailed study in the early universe. So we investigate the intrinsic property of this unique system. So assuming a celsic profile and fitting routine between the image and source plane, we find that a subregion of the galaxy is crossing the caustic line, which is stretched out to the elongated shape observed as the arc, while the other multiple images traces the whole region of the galaxy in the source plane. The magnification factor is estimated to be around 20 and even 160 at the arc. Also, such high magnification has large uncertainty in general, but it is not the case in this system with two reasons. First, the configuration of these multiple images works as a strong constraint, so the estimate wouldn't be easily changed. And second, we confirm these interpretation and magnification values with independent 3-lens models constructed by 3 independent modelers in our team. So we think that the high magnification values in this system would be much more robust than usual. So here summarizes the physical property of this system after the lens correction. So 3 times fainter than the characteristic luminosity, both sub and 4 regions of the galaxy are falling on the main sequence of star formation and stellar mass relation. And based on 3D modeling results, we also obtained the dynamical mass and subsequently gas mass by subtracting the stellar mass from dynamical mass estimate. The gas mass and the galaxy size estimate show the average value among the typical star forming galaxy at redshift 6. So we conclude that this strongly dense galaxy is an abundant and representative population of the sub-L-star galaxy at redshift 6. To see the direct observed picture in the source plane, we also performed the pixel-to-pixel source plane reconstruction. First, for one of the multiple image which trace the whole region of the galaxy. Since we find several clamp features there from the HST map, those are marked from A to D. And the right panel shows the source plane reconstructed map. The white ellipse here corresponds to the source plane HST resolution, showing that we achieve a few hundred parsec scale resolution in the source plane. Next, for the arc, we obtained the reconstructed map presented in this inset panel, where the lens corrected luminosity reaches down to about 1% of the bright peak of the whole region. Interestingly, we find that this luminosity distribution from the arc perfectly matches with the position of a faint clamp seen here, WE. So this is away from the UV brightest peak by 1 to 2 kiloparsec from the brightest peak of the galaxy. So this nicely illustrates the power of the lensing, making even the faintest outskirt emission highly visible, which is almost invisible in the reconstructed map from other multiple images even with the magnification factor around 20. The C2 line distribution are also reconstructed and find that its effective radius is 2 to 3 times more extended than the rest frame UV one, while the C2 line peak positions are consistent within the errors from the UV peak position, both in sub and whole region of the galaxy. So based on the current data depth and resolution, we conclude that the majority of C2 line arises from the rest frame UV emitting regions. Thanks to this unique system, we investigate the spatially resolved C2 line and star formation relation. So after the lens correction, we find that both sub and whole region of the galaxy show the relations consistent with the local galaxy relation within the dispersion. We also measure the rest frame UV sizes and plot the C2 line over the star formation ratio as a function of the star formation surface density and compare with another spatially resolved results obtained from the dusty surface galaxy at redshift 3. So these plots are known to have an anti-correlation, which is explained that the abundance of singly ionized carbon and its emissivity are saturated in the highly ionized state region at the high star formation and surface density region. We find that subregion shows a slightly higher value, which is consistent with this known trend. So this slightly higher C2-line emissivity in the subregion of the galaxy would be explained by the sufficient offset from the UV brightest center, which makes the ionization state at this subregion keep moderate. So we have studied the cold ISM property with ALMA. So what's next? We are really happy to be informed that our follow-up JWST program targeting 2 brightest multiple images is approved in cycle 1. So by using the near-term deep imaging and near-spec IFU, and thanks to the brightest property so far confirmed at redshift over 6, we will achieve the full characterization of early galaxy assembly with ALMA and JWST. The tool means that we will study from young all-star population that's obscured and obscured star-forming regions, cold and hot ISM, and also the dark matter components. So here we break down in 3 key goals in the JWST program. First, the detailed structure. The detailed structure of individual star-forming clump will be investigated down to 20 to 80 parsec scale resolution in the source plane. And the second, we study the spatially resolved internal physical property of a typical star galaxy at redshift 6, such as DPT, electron density, and the metallicity gradient. So this spatially resolved characterization will be important itself, but it will also provide the key insight on what physical mechanism causing the large diversity in the C2-line property, for example. And third, we will study the detailed kinematics by using a bright optical line from ISM to the circumgalactic medium scale, including the motion of individual clumps in falling and outflowing, and also testing if there is a drop in the rotation curve at the outer area, which constrains the dark matter concentration in a typical galaxy at redshift 6. So in this way, also with the ALMA data, we will fully characterize the representative survey of the galaxy at redshift 6. So please stay tuned. So here is a summary. The ALMA Lensing Cluster Survey is uniquely exploring the faint 1 millimeter regime and discovered a strongly lensed multiple image C2-line emission from a representative survey of the galaxy at redshift 6. The HST and ALMA images map out the structure down to a few hundred parsec scale in the source plane, and the transformation relation and relation is consistent with the local galaxy from spatially resolved and whole galaxy scale. And JWST program is also scheduled, and we will fully characterize the key component of the galaxy, early galaxy, also together with ALMA. So stay tuned, and thank you for listening.
Great, thank you so much, Seiji. So let's give folks a little time to ask some questions, and then we might have only time for one before we move on. Okay.
There's one question in general. How many more sub-L star galaxies do you expect to find? I don't know, I'm assuming in your data set.
So for starburst galaxies, sorry, C plus emitter?
Sub-L star galaxies, if you can detect any.
In terms of the redshift, intermediate redshift, we also identify many long arc-shaped, elongated shaped lens galaxies. So we will, let's say 10-ish strongly lensed continuum sources we already identified. But in terms of the such strongly lensed C plus emitter, at the current stage we only have one.
Great. That's really beautiful data on this source. So please, if you have more questions for Seiji, please put them in the Slack. And we might take this time to transition to our last speaker. And Seiji, you can answer any more questions. I'm sure they'll come in.
Yeah, thank you.
There. Thank you, Seiji.